Okay, let's talk about Module 3. Module 3 is about AC fundamentals, and obviously it's an important module to understand the fundamentals of AC electronics and ultimately AC bulk power systems. So here we have just a picture of a simple circuit, which we're going to get into as we get into it. But as far as the objectives for this module, number one, we want to state Faraday's law. We want to know and understand what Faraday's law is. It's a very important fundamental concept in AC power systems. And explain how magnetism of AC current creates generation, explain the mechanism of AC current towards generation. And we're going to talk about that, and that also ties into Faraday's law. We want to explain the characteristics of the AC sine wave, which we've already talked about to some degree already. And we want to discuss capacitors and their role in AC and DC circuits. There's a picture of a capacitor next to that C. That's a little component you might see on a circuit board, for example. We want to discuss inductors and their role in AC and DC circuits. You can see that coil or an inductor next to the coil symbol with the L on it. And that's has the same effects on big bulk power systems as it does on small electronic circuits. So understanding it on the small circuits to kind of help us understand on the large ones. Then we want to explain how resistance, capacitive reactance, inductive reactance, and impedance all kind of come together. That's a little complex, but understanding that will help you tremendously if your goal is to get into big bulk power systems and understanding, where we talk about capacitive reactance, inductive reactance, we talk about reactance reserves and VAR flow and all that stuff, all those things, impedance, reactances, all of those concepts we're going to talk about here in this module that do apply later on as we get into more advanced power system concepts. Okay, we're going to also explain how the transformer works. And a transformer is basically like two inductors next to each other. So we're going to talk about, magnetic fields and things going from one inductor to the other, causing a transformer type reaction. So we've got quite a few things to talk about in this subject, and then it kind of boils down to what's referred to as power factor and how it is used. So we'll get to know the terms around power factor as well. Okay, so starting out with DC, we know that we have a constant voltage and a constant current. That's DC. We know how we have a DC voltage source, like a battery. Now we talk about alternating current, or AC. We're talking about where the electrons aren't going in a circle and stay in a circle, and whether it's clockwise or counterclockwise like you would in a DC circuit. Now they're going back and forth. It's going back and forth. The current is reversing itself 60 times a second, okay? The symbol for the voltage source for AC has the sine wave in it. So you have a battery versus a sine wave or an AC source. Okay, now we have a magnetic field issue where we have a north and a south pole. We have the same concepts as we did before, like poles repel and opposite poles attract. So we have the same situation there. So a compass aligns with the lines of force like this. You see the compass needles in the drawings. And like poles repel. Okay, that's something that we're familiar with. Now, when a current is flowing through a conductor, it produces a magnetic field. Okay, there's Lenz's law and a few others that come into play there, Ampere's law. But when the current is flowing through the conductor, you can see the little symbol I. When the current is flowing through the conductor, it creates rings or circles of a magnetic field all the way along that inductor, okay? That is a fact of life. Current flows through a wire, there's a magnetic field. Accept it. Just like gravity. You accept gravity. It's there. It's a fact of life. It's a physical law. Current flowing through a conductor creates a magnetic field. That's a physical law, okay? Faraday's law is a voltage is produced in a conductor when it is exposed to a changing magnetic field. the induced voltage is proportional to the rate of change of the magnetic field. Okay? So coils that are moving or rotating inside a magnetic field, coils that are rotating in a magnetic field, okay, will generate a voltage from Faraday's law. Or you can have the coil stationary and have a moving magnetic field and create a voltage. Doesn't matter. Long as there is a relationship of change between the magnetic field and the conductor, Faraday's law says that a voltage will be produced on that conductor. Okay? Now, here's an example where you have, here's a coil of wire that is rotating. It's spinning around and you have magnets on both sides. If we take the coil of wire, it will actually produce a changing magnetic field here, causing a voltage to occur. So if we take a generator and somehow move or rotate the shaft, and we have fixed magnets, we will produce AC voltage. Okay? That's a Faraday generator. That's Faraday's law. And that is a voltage is produced on any conductor in a changing magnetic field. We've created a changing magnetic field because we're rotating the coil. We could have a fixed coil and rotate the magnets to do the same thing. Okay. So mechanical energy, rotation, creating an electric voltage output. Okay? We have stationary magnets. Now, here we have electric power system. That happens to be some generators at Hoover Dam in the picture there. And here we have a rotating magnet. Okay, the magnet's what's rotating, and we have stationary coils, which is exactly the opposite of what I just showed you. And it still produces the AC sine wave. So what we have here in this picture of this generator is the generator is vertical, and the shaft is rotating because the water flowing down below. It's rotating the shaft. We have coils on the outside, and the center rotating shaft has the magnet. And the magnet is spinning, causing voltage to be produced. Generators at major power plants use stationary conductors with rotating magnetic fields. Okay? And if we were to take that generator and put it on its side, it'd be like a regular power plant generator. We'll get into that too. So here we have Faraday's law. Faraday's law works both ways. Either the magnet is stationary and the conductor is rotating, or the conductor is stationary and the magnet is rotating. Doesn't matter. Okay. Now, characteristics of the AC sine wave, a little bit more than what we talked about earlier. Here we have a positive peak and a negative peak. We have one complete cycle here called period of T. We have, if it's 180 degrees and 360 degrees, we're talking about a phase between this point and this point will be some degrees, referred to as a phase angle. And we have peak to peak. Okay, so there's a couple characteristics of AC that has to do with the degrees in a circle. The amplitude. There's a peak value and there's a peak to peak value. We talked about this. And there's also an RMS value. Okay, so the phase angle is really the phases between 2 points on the sine wave. And we're going to be talking about phase and phase angle many times as we move through these courses. It could be phase angle between substations, between power, between utilities, and phase angle between a system and a generator when you're connecting them together. There's different kinds of phase angles. So keep in mind, phase angle has to do with the degrees in a sine wave curve like this. All right, period. The period of time to complete one cycle. If the frequency, like in the first one, the frequency is 1 hertz or 1 cycle per second, then it takes 1 second to complete a cycle. If the frequency is 2 hertz, it takes 2 seconds to complete the cycle. So 1 cycle takes a half a second. Just some fundamentals. Okay, so that's our frequency versus time. Okay? And that little formula in the center that just popped up, the frequency is the inverse of time. Very true. It's true. If the frequency is so many cycles per second, then the time is so many seconds per cycle. Makes sense, okay? in radio and communications, what have you. You think of the frequency domain as being spectrum analyzers and the time domain being oscilloscopes. Depending on what you're looking at, frequency or time, you would use one or the other. Okay? So they're related like this. All right. Next thing to think about is phase relationships. Here we have voltage and current in a phase relationship. Here the voltage and current are in the same phase. They're in phase. When the voltage gets greater, the current gets greater. When the voltage gets less, the current is less. They are in phase. And that only happens in resistive circuits. You put a capacitor and inductor in there, changes that. Resistive circuits, the voltage and current are in phase. Okay? In AC circuits where you have out of phase, where the current is out of phase of the voltage, that happens when you have conductors which the current lags or capacitors where the currents lead. And we're going to talk about that because when we have a phase angle between the current and voltage in AC power systems or in AC systems. So this is very important to know that there is a lead or a lag in current depending on whether it's inductive or capacitive circuits. Okay? In this particular case, even though they're out of phase, the current is leading the voltage. The current has started going up before the voltage did. And therefore, it is a leading circuit. And we can say that the current, excuse me, I said that all wrong. I need to back that one up. Do I have to do the whole slide over?
You don't need to. Just remember wherever you know that you had that you were at.
Okay, I'm going to back up here to here, and then I'll start the new part.
Sure.
Okay, when we talk about voltage and current being out of phase, the current could either lead or lag the voltage. And there's a phase angle associated with the lead or the lag. And the lead and the lag comes from whether the circuit includes capacitors or inductors. Inductive circuits, the current lags the voltage. In capacitive circuits, the current leads the voltage. So here we have a situation where if the current is lagging or the current is leading, will tell us which the circuit is primarily inductive or capacitive. Okay? So voltage leads current because it raises, from 0 volts earlier than the current. So here we have the voltage is starting to increase, and then the current starts to increase at that phase angle later. Okay? Now, we can also see that the current, is lagging the voltage because first you had the voltage, then you had the current. Okay? So this is a current lagging, which would be indicative of an inductive circuit. Okay, now when it comes to capacitors, a little symbol, little picture of a small capacitor there, and you can get it at Radio Shack or something like that. You see them on electronic circuits all the time. Capacitance is measured in farads, and the capacitance has to do with having two conductive plates separated by some gap. And how big the plates are, the distance between the plates, all those physical dimensions gives a capacitance calculation. You can determine the number of farads by the physical dimensions of the component itself. Okay? So when we look at the surface area of a capacitor and the distance between the plates, the size of the plates, the dielectric material between the plates, you can calculate what the capacitance is of a capacitor. Okay, it's physical. Okay, the capacitance increases by increasing the size of the plates, decreasing the distance between the plates, and using dielectric materials with greater insulating characteristics increase capacitance. Okay, so we might fill the capacitor with paper or mica, ceramic, what have you, and get different dimensions and different sizes to come up with some fixed capacitance which is measured in farads. Okay, so capacitors in a circuit. When you have a capacitor in a circuit, and you apply a voltage to it, immediately the capacitor has to charge up. So the current rushes to the plates of the capacitor to charge up the capacitor, to charge up the dielectric in between the two plates. Current is just screaming out fast as it can to charge up that capacitor. So the voltage on the capacitor takes time to build up. So the current is out there charging up the capacitor. The voltage on the capacitor lags the current because you need the current to charge up the capacitor before you get a voltage. So the voltage is lagging the current, or the current is leading the voltage, however you want to say it. Since voltage is normally our standard, we start with voltage like a generator in plant. On a blackout, we're starting up the restoration of a power system. First thing you do is turn on the generators and get voltage. Since we use voltage as the reference, we would then use that in this case and say that since voltage is a reference, a capacitor the current leads voltage. We wouldn't say the voltage lags the current. We would say the current leads the voltage because we keep voltage as our reference. So a capacitor, the current leads voltage. Okay? Now, in a capacitor, current leads by 90 degrees. Okay, that's a pure capacitive circuit. It shows you the symbol here, the angle. When when the blue is the voltage and the source, and the red is the voltage on the capacitor, and if you can picture those two vectors kind of rotating counterclockwise, the blue would be going up to the north before the red. Therefore, we have a positive 90-degree angle there. All right. Now, here's where it gets a little tricky, but I want you to understand it. It's not impossible to understand, but when we start talking about reactance, capacitive reactance, inductive reactance, and then resistance, so there's resistance, capacitive reactance, inductive reactance. You put all of that together, you get impedance. Okay, so I want to kind of get those concepts down to you. Capacitive reactance. Okay, the measure of the opposition of the current flow in an AC circuit due to a capacitor. Okay, this is the same definition as a resistor, therefore it's measured in ohms. So when we talk about capacitive reactance or inductive reactance, it's measured in ohms, just like resistance is measured in ohms. And therefore impedance is measured in ohms. Okay. Formulas look ugly when you first see them, but they're not bad. X sub C, the capacitive reactance, is 1 over 2 pi times the frequency times the capacitance in farads. If you don't want to get into how that formula is derived, but I just want you to know if it's a 60 hertz number, then a 2 pi f turns out to be 377. That becomes a fixed number. So that 1 over 2 pi f is a fixed number for a 60 hertz system. It's a different fixed number if it's a 50 hertz system. But since it's a fixed number, a constant, then the capacitive reactance changes with the amount of farads. Okay? So if the farads increases or the capacitance increases, the capacitive reactance decreases. So capacitive reactance is inversely proportional to the frequency. The smaller the frequency, the greater is the opposition to current flow. Okay? So here we have a resistor and a capacitor. Now, at very low frequencies, DC components of frequency, like if the frequency is 0, a capacitor in series with a voltage source has an open circuit effect. In other words, at 0 frequency, if you look up at that formula, if f is 0, well, you can't divide by 0 because the number is infinity. Well, if it's infinity, that means infinite. That means there is no resistance. So it all makes sense. So what happens is when you have a resistor in series with a capacitor at 0 frequency, a capacitor looks like an open circuit. On the other hand, at very high frequencies, the capacitor looks like a short circuit. At very high frequencies, then 1 divided by a big number turns out to be a really small number. Therefore, it looks like a short circuit. So at high frequencies, the capacitive reactance is essentially 0, and it looks like just a resistive circuit. So when you're looking at circuit diagrams, if it's a low frequency, capacitors are opens. If it's a high frequency, capacitors are shorts. So you can kind of cut down on the amount of components you're trying to analyze. Now it's opposite for inductors. Inductors, coils. Okay? Now they oppose changes in current. In other words, if you take a motor and you start it up, it takes time for a motor to build up. Well, why is that? Well, the current has to build up a magnetic field before you can have something spin. So you put current in to create a magnetic field, right? Because current creates a magnetic field. So you got to get current going before you have a magnetic field before the motor will start. So you end up with this lagging effect, and let's talk about that. Inductance, measured in henries. If you went to Radio Shack and picked up an inductor, it will tell you how many henries it is. Okay, henries, that's a physical thing again. How many turns? What's the size of the wire? What's the spacing between turns? What's the diameter of the air around the turns? All that physical stuff creates the number of henries. Okay, so it's a physical thing. So when we look at a coil, you know, what's the spacing? What's the core made of? What is the number of turns, the space between turns, diameter? All that gives you so many henries. So the inductance increases by increasing the number of turns, by decreasing the space between turns, by increasing the cross-sectional area of the core, using material and with magnetic properties for the core, like iron core, and you'll come up with different types of cores used with coils to change the magnetic characteristics of the inductor. Okay? Now, how inductors relate with voltage and current. Now, inductors in an AC circuit, their current is going to lag the voltage. Now, here's a circuit that shows pure resistance here, or excuse me, pure inductance. And in this case, when we have a voltage applied to the inductor, and our current here, see where we have is a 90 degrees lag between the current of the inductor and the voltage on the inductor. There's a 90 degrees in a pure circuit like this. So the main thing to understand here is that in an inductive circuit, the current lags the voltage. Okay? And you know, in a pure inductive circuit, it lags as much as 90 degrees. We usually don't get that much lag because we have resistance in the circuit. Maybe even the ohmic resistance of the wire itself would reduce it. But pure inductance is 90 degrees. Okay, and that's what shows the inductor voltage 90 degrees ahead of the inductor current, and that little symbol on the right there of your screen. All right, when it comes to reactance, remember we just learned capacitive reactance measured in ohms. Well, inductive reactance is also measured in ohms. And when you have inductive reactance in ohms, where does that come from? Okay, well, X of L is equal to 2 pi FL. Remember that 2 pi F, which is 377 if you had 60 hertz, okay? And L is the inductance in henries. So that first, the 2 pi F is a fixed number. So if you increase the L, you increase the inductive reactance. So let's look a little bit more about this. X of L is proportional to the frequency. The greater the frequency, the greater the opposition to current flow. In other words, if frequency increases, since X of L is in ohms, the X of L increases, and it's like having a bigger resistor. Okay? So if we take a resistor and put it in series with an inductor, and at very low frequencies, okay, F is a small number, therefore X of L is a very small number, and if F were 0, X of L is 0, that means at very low frequencies, the inductor looks like a short circuit. 0 resistance. Okay? And at very high frequencies, X of L is a huge number. And if it's very high frequencies, then X of L is almost infinity, and therefore X of L is an open circuit. Okay, so when you have high frequencies, an inductor looks like an open circuit. I could get into a lot of examples like this. Power line carrier on power systems. You know, when you have inductors in there, it blocks the high frequency radio signals, but yet it still passes the AC power. We'll get into that with communications, you know, in another module. Or with high frequencies, inductors look like open circuits, capacitors look like short circuits. Then you say, okay, if I have a grounded system or a non-grounded system, you know, if I have high frequency versus low frequency, and I have a problem with a transformer, and let's say it's a delta transformer, for example, I know we'll learn about this more later, and there's no ground. Well, that tells us that it's an open circuit for fault currents, or if it's a grounded Y transformer, we'll learn more about later, then we have a ground path for fault currents. So whether an inductor or a capacitor, when you're analyzing these things, I just want you to think of it this way. Capacitors at low frequencies look like open circuits, and inductors look like short circuits. At high frequencies, capacitors look like short circuits, and inductors look like open circuits. And therefore, get the concept that they act opposite of each other. The beauty is, if you can put a capacitor with an inductor, you can cancel that opposition out and end up with a pure resistive circuit. And we do that, okay, in power systems. So just to kind of get you a little bit ahead. All right. When we combine resistance, inductance, and capacitive reactance together, you get impedance. So we'll get to the formula. So there's capacitive impedance, is inductive, you know, impedance. But when it, oh, this particular little slogan here that I should bring up helps you remember. Eli the Iceman. When you're trying to learn impedance, remember we're talking about inductors and capacitors and leading and lagging. Now Eli, E-L-I, E is for voltage, L is inductance, and I is current. Eli says that the voltage leads the current in an inductive circuit, Eli, okay? And the Iceman says that C is for capacitor. Now we have I for current and E for voltage of the capacitor. So ICE says that on capacitor, the current is before the voltage. So Eli the Iceman kind of helps you remember that, you know, voltage leads in current in an inductive circuit, and current leads voltage in a capacitive circuit. So voltage, Eli the Iceman, okay? So hopefully that kind of helps you a little bit. By choosing the size of the components, we can zero out the phase shift, obtaining a circuit with purely resistive characteristics. Voltage and current are in phase even though the inductors and capacitors are present. And that's something that's very interesting, as you will learn as we go on. That if we want to reduce losses in a power system and we have a lot of inductance in the wire, we add capacitors to the conductors so that the capacitance and the inductance cancel out and the wire looks just pure resistive, and that makes the line look electrically shorter. You know, we use this concept a lot in power systems. If you build a power plant, you know, 400 miles away, and you got these long transmission lines that have a lot of resistance and inductance, and if we put in series capacitors, the series capacitor compensates for the series inductance of the wire. Therefore, the 500-mile line could look like it's a 200-mile line because you removed a lot of the electrical characteristics. That's what we're learning about here, is being able to, you want to trick or play with the system, however you want to call it, to represent something better than it is by just using knowledge that you're learning here. Okay, so when we want to talk about quantities, total impedance, Z is the symbol for impedance. It's equal to the square root of R squared, resistance squared, plus or minus X sub L minus X sub C squared. Now, that should be X little l and C little c, so it matches the previous, but slides, like down below in the table, it shows little c's and little l's. Okay, the idea is since inductive reactance and capacitive reactance can cancel. And if you made those reactances equal, then that component in the square root symbol there goes to 0, and then the square root of r squared becomes r. So the impedance of a circuit actually becomes the resistance of a circuit when x sub L equals x sub C. Okay, I hope you got that. Now in radio communications, you create x sub L equal to x sub C, and you could take any inductor, any capacitor, figure out its x sub L and its x sub C, make them equal, and find out the frequency that makes them equal. You can solve for F. And when you solve for F, that's the frequency we call the resonant frequency. And that's how radio frequencies work. And radio and TV and everything else works on wireless radios when you make those two equal at a certain frequency. Change frequency, just get a different inductor or different capacitor. These are just little things that kind of help you understand, you know, reactance, and then I just threw in resonance. But resistance, okay, now we take that table. You got resistance, you have R, and R, you know, the resistance here, R for resistance, power is in watts, the units are in ohms. When we take inductive reactance, X sub L, okay, we're still ohms for units, but now we're talking VARs. VARs. Now what is power equal to? Voltage times current. VARs is a form of power. It's called voltage times current, VA, reactive. VA, volts times amps, reactive. VARs. Okay, now inductive reactance is a positive R, and capacitive reactance is a negative R. So in terms of power, we have watts, plus VARs, minus VARs. In terms of units, they're all ohms. Kind of confusing. But impedance is when you have an R, whatever the sum of the x sub C and the x sub R, x sub C and the x sub L is, and that's supposed to be squared, gives you the watts and VARs, plus or minus VARs. And one thing very basic in AC that you should be aware of, actually this is what I did my master's thesis on, was when you, in a power system, you have both watts and VARs flowing. When you look at any power system diagram and you look at real-time operations, you have watts flowing and VARs flowing. And just like Kirchhoff said, the current equals 0. Well, that's true with watts and it's true with VARs. You can think of all the watts have to add up. You have all the generation of watts, you have all the watt losses in the lines, you have all the watt loads. Well, all the watt loads and the watt losses must equal the watts generated. Same with VARs. The VARs generated, whether they come from generators or for capacitor banks, must equal all the VARs consumed, which would be like coils and transformers and those types of things. So in a power system, kind of think of it as this way. You have apples and oranges flowing all the time. Apples being the watts. They're all flowing however they flow, and you have all the VARs, and they're all flowing however they flow. Okay? So at any moment in time, you have watts and VARs. Now they complement each other, they help each other, they can hinder each other. If you don't have enough VARs, you could have voltage collapse. If you could, and then you have problems that way. So you have reactive reserves. You're going to start picking up all these terms as you go through these courses. This is a fundamental course. It's trying to give you a foundation. And when it comes to impedance, like we're talking about here, this pretty much puts the power lines and the transformers and the capacitor banks and all that stuff into perspective that they have. We're dealing with ohms, but we're talking about in power, watts and VARs. Plus or minus VARs, that can cancel and give just watts. Okay? So, just a little bit of added information on this particular slide when it comes to impedance on AC circuits. Okay, and the formulas here for capacitive reactance and inductive reactance. Okay, and I think we covered those pretty good. When we put it all together, what do we get? we have resistance on the horizontal, and we have the capacitive and inductive VARs on the vertical. Now, if we were trying to draw impedance, this is how you would do it. You have if you have the real resistance, okay, here, the watts and the VARs. Now remember, the VARs can cancel out and become just watts. So here's a case where we have resistance of 3, we have a net VARs of plus 4, we had some capacitive here. See, if you go back here, if you take this and go back to this and subtract it off of here, that much to here, what you're left with is some inductive VARs. Now, if this is 3 and this is 4, and you go 3 squared plus 4 squared, square root of that is 5, then this becomes 5. This 5 is known as VA, and we're going to get into that here shortly. If we want to calculate the angle, now we've got to go into trig and say that the angle is the arctangent of x of L divided by r, 53 degrees. Okay, a little bit of math there if you wanted to or needed to calculate an angle. The important part here is if this is r and this is x, this is z. Okay, that's the impedance. Overall, now you can describe the impedance two ways. You can say it's a magnitude of 5 with 50-degree angle, or you could say it's R3 or X3 and Y4. So you can do the coordinate system, saying it's a x equals 4 and a y, x equals 3 and a y equals 4. Or you can call it in polar coordinates, magnitude of 5 and a 53-degree angle. So that's kind of what we're talking about here when it comes to impedance. You know, it's the combination thereof. And when we talk about in terms of power, this is watts, this is VARs, this is VA. Okay. Now we're going to talk about what I just said in power. Okay. In power, we have watts, we have VARs capacitive, VARs inductive. Okay. And now we have watts resistance. That would be like a toaster or something of real resistance. And then we have net VARs inductive giving a VA. Now the VA is power also, volts times amps, but is peak volts times peak amps. Remember the peak curves? Peak volts and the peak amps. You multiply the peaks times the peaks, even though there might be a phase angle between them because of leading and lagging. The peak times the peak, that's the VA. Okay? And then we have made up of watts and VARs. For an example, here we have 30 megawatts of power here. We have 40 megavars of inductive reactance, and that would be 50 MVA. So if we had a 50 MVA transformer, we could load it up with 30 megawatts of watts and 40 megavars. The problem is, the power companies usually don't get paid much for VARs. Okay, their revenue meters, or kilowatt-hour meters, don't really turn for VARs. They're watt meters, not VAR meters or watt meters. So if they invested in a 50 megawatt or 50 MVA transformer, they'd want to put 50 megawatts through it, not 40 megavars. So they would add capacitors to knock that down, so make that number come down, so then they could have 50 megawatts for a 50 MVA transformer. Now they're making money. Okay, and one of the last terms to know in AC fundamentals is this term called power factor. And power factor is the real power divided by total power, or the watts divided by VA. Now I'm going to switch back to the previous slide for a second to show you something here. The small number divided by the big number. The watts divided by the MVA. The watts divided by the the MVA, or the watts divided by VA, is power factor. Okay? And that's just a term used. And it's very, very commonly used, power factor, because you want the power factor to be unity. You want all the power being consumed to be watts, or the power generated and transmitted to be watts. So power factor is an important efficiency determination in AC power systems. Another way of looking at power factor in AC systems is using a little analogy here of a river. Here's the shores of a river, and let's say you wanted to get from point A to point B. So the minimum amount of energy it would take to get from point A to point B is a straight line. But let's say there's a current flowing in the river that's opposing you, 90 degrees. Now you got to go to point C before you get to B. You're really trying to get to B, but because of the interference, you've got to put more energy out in order to accomplish your goal. So extra effort, extra energy, that's what happens. Same thing is like if flying in an airplane. If you're flying from San Diego to Atlanta, Georgia, you want to go straight across. Well, if there's a wind coming down from the north, you got to turn the plane towards the north a little bit just so you can fly straight. Well, now your cross-sectional area is more wind resistance, going to take more fuel, you're going to fly slower, all because of that northerly wind that's coming down on you. Same is true in power systems. If you don't get the VARs right, you're exerting more energy, wasting money, wasting time, those types of things. Okay, now we're going to talk about a transformer. Transformers work with AC only. So what happens is in a transformer, what we're doing is we're putting a voltage and a current into a coil on one side, and through the magnetic field, and sometimes with a core so that we can increase that coupling, we have another coil on the other side that produces a voltage and a current because of Faraday's law. We have a changing magnetic field from the current of this coil, because it's an AC circuit, creates a changing magnetic field, back and forth, north and south, which imposes a voltage on a coil over here to produce a voltage on the secondary side. The nice thing about it, the voltage on the primary to the voltage on the secondary has the ratio of the turns ratio. Okay, in this particular case, I'm not sure what the winding ratio is. It looks like maybe 2 to 1. So if I put 100 volts over here, 2 to 1, okay, I'll get 50 volts over here. Okay, so that's what a transformer does. It uses Faraday's law to put if you reverse this, we put a low voltage on, if we put a voltage on a low voltage side, we will produce a high voltage side. And when you increase the voltage, you reduce the current for the same amount of power. If you go in this direction, if you decrease the voltage, you'll increase the current because it's got to be the same amount of power. So that's characteristics of a transformer. A transformer transforms the voltage of the source into the required value for the load by simply selecting the appropriate turns ratio. Now, think of this. Why do we put transformers in a system? When you have a power plant that's putting out high power, if we want to get that power to another location several hundred miles away, we want to increase the voltage to reduce the current. The I squared R loss is significantly dropped so that you can get across a long distance. And at the other end, you put a transformer in backwards so that the voltage, the high voltage, gets reduced to a lower voltage so you can get all your current back for distribution. So that's what we do. We try to raise the voltage as high as we can and reduce the current therefore. And then what we'll do is even on the high voltage transmission lines, we'll put multiple conductors to get even more current to flow while we built the right-of-way and got the transmission towers and everything else. So transformers are used to step up the voltage for long distances and then reduce it. Okay, so here we have a transformer. And we have, VP is a voltage in the primary. And we have voltage in the secondary. Okay, and because of the turns ratio, we can have a different voltage in the secondary. We'll have a current in the primary and we'll have a current in the secondary. Okay, NP is the turns ratio in the primary and S is the number of turns in the secondary. So now, the voltage relationship is this. The voltage between the primary and secondary has to do with the number of turns in the primary to the number of turns in the secondary. Very simple. If the number of turns in the primary to the secondary is 10, then the primary is 10 times the secondary. Just simple like that. The current is the opposite. Look at that. The current in the primary and the current in the secondary is the reciprocal of the turns ratios, which makes sense. Because if you're going to raise the voltage, you've got to lower the current. Or if you're going to raise the current, you've got to lower the voltage. So that voltage times current stays the same. It's a transformer. Very important. Used in the power systems all the time to raise the voltage or reduce the voltage and consequently the current. Now, a step-down transformer is when the number of turns on the primary okay, is greater than the secondary. Okay, the voltage in the secondary is smaller. Okay, and the voltage in the primary and the current flowing in the secondary is greater than the current in the primary windings. The power stays the same. Basically, what I just told you. You know, whether you're stepping up or stepping down, usually a step-up transformer is just outside of a power plant, and step-down transformers are in substations. Okay? So a power primary is equal to the power secondary. Therefore, the high voltage, low current equals the low voltage, high current on the secondary. If we have 480 volts at 1 amp in the primary, and we have a 4:1 turns ratio, we're going to have a 120 in the secondary allowing 4 amps to flow. Because 4 times 120 is the same thing as 1 times 480. If you get that fundamental understood in this training, the transformers, the current and voltage and the reciprocal like that, you'll understand why there's so many transformers in the power system, and this is fundamental AC. Okay, so you can see the calculations. 480 times 1 is the same thing as 120 times 480. Excuse me, 120 times 4. Okay. When it's the opposite, power still equal. Now we have low voltage on the primary, high current. That would be a case where the output of a generator is usually low voltage with high current. We want to step that up. Okay? And then we have a secondary that has a high voltage, low current. That would be feeding a transmission line. Same example, 120 on the low voltage with 2.5 amps with a 1:5 turns ratio gives you 600 with a half amp. So we're stepping up the voltage to reduce the current to lower the transmission line losses, if that's why we're stepping up the power. All right, now let's summarize what we learned in AC fundamentals. This is very important, this subject. If you're going to go on to be system control operators or go and work in a power industry or distribution, or if you're going to work in any aspect of electric power, you need to understand the fundamentals that we just talked about. So in summarizing this module, number one, we explained what Faraday's law was. That's where a voltage is produced on any conductor in a changing magnetic field. We explained the mechanism of AC current generation. We talked about how we have a spinning magnet or a spinning coil to produce voltage. We explained the characteristics of the AC sine wave, how we have the phase angles and the period and the frequency. We discussed capacitors and their role in AC and DC circuits, what a capacitor does and how it is open for high frequencies, or excuse me, for low frequencies, and a short for high frequencies. We talked about inductors in their roles in AC and DC circuits and how they look like short circuits for low frequencies and open circuits for high frequencies. We explained the relationship between resistance, capacitive reactance, inductive reactance, and impedance. Remember, we went into the equations where we had plus or minus X of L and X of C, and I was telling you that everything is in ohms. Resistance, capacitive reactance, inductive reactance. And we talked about the graphs and the watts and the vars. Okay? We explained the operation of transformers and related formulas. Step-up transformer, step-down. What are we stepping up? Voltage. What are we stepping down? Voltage. And the current is the opposite. If we step up voltage, the current steps down. Okay? We learned about transformers, how important they are in AC power systems. So hopefully this helps you understand the concepts, and also one more about power factor, how important it is to know your efficiency of your system. You know, what's the total number of watts versus the total power either consumed or produced. You want to know the power factor of a load? It's how many watts versus total power consumed. So these are the AC fundamental important features that you need to know moving along. Thank you.